And therefore, there are skeptics of quantum computing who say that you can never get there as a matter of principle. And there are some, I'm not saying that only is taking that particular thing. Others who are divided in their opinion. And there are, of course, votaries and the hyperactive hypers of the field. So, what provoked this thing is the recent controversy that was set up by Jensen Huang's statement that quantum computers are not going to be realized for the next 2 decades. People like Scott Aronson took exception to this, many others joined in. And I pitched in saying that if the stock market fell, it is not because of Jensen's statement, which is a fair assessment of the field, but it's only because of the extraordinary hype surrounding this. And we slowly realized, Google Willow claim notwithstanding, that we have a steep path ahead. I'm neither a skeptic nor a votary, so I'm still a fence sitter, and I present what I understand about Google's claim and what you should make out of it and what you should not make out of that particular thing. So I present to you quantum batting beyond Google Willow. Of course, you know, the Willow, as a cricket-loving nation, is the preferred wood for our batting. And whether the Google Willow will be able to bat right up to the full distance of making quantum computers which can do the job. And the claim of quantum supremacy is certainly an empty claim. It is perfectly useless to say that quantum random circuit sampling is of any practical use, other than keeping the interest alive and saying that, look here, we are still in the game, we are still doing it, don't let the stock market fall down, type of thing. And, but that statement notwithstanding, there are remarkable achievements as far as hardware is concerned. There are remarkable achievements in terms of error correction is concerned. And I will try to give a balanced presentation of that. So if you whisper when the wind blows, so your branches below, we will listen for a day, a week, a year, till we know that what willows say, what willows speak. So what is the willow speaking to us is something that I will take up for discussion today. So let us look at the hardware. Much of these terms, for those who are not initiated, will not be very obvious. I hope to clarify what these terms actually mean. Willow hardware is a superconducting qubit, transform qubit of 105 qubit processor. And today it's not a race about how many qubits you make, because one of the frustrating things in our earlier engagement with NQM on the Quest is that people are saying that progression is about from 10 qubits to 50 to 100 to 200 and sort of a thing. That sort of a qubit growth is not the only thing that is important as far as quantum computers is concerned. This was quickly realized by IBM and Google that without error correction, the noisy intermediate scale quantum computing will not be at all useful. These are, in some sense, as automated subpolynomial, and therefore they are not even good enough to do what classical computers do, unless you do error correction. So, in this claim, it takes 10 septillion years, 10 power 24, what a classical computer would take, and it is done in 5 minutes in the quantum. The quantum computer is a process. In the sense, if you are doing a random circuit sampling, I will come to that, you take randomly some part of the circuit, and then repeatedly do a measurement, and then sample from this distribution. So it's not computing anything specific. It is just being what it is. It is like water flowing, and then you rush the water faster, then it will go into turbulence, and that sort of a physical process is what's happening. So what you're trying to compare is a physical process, which is a quantum computer, notwithstanding the classical support I will come to it, and then looking at a computational problem done by a classical computer of trying to simulate quantum mechanics on a classical computer. This is the type of comparison. So you should take with a big pinch of salt this sort of a 10 septillion years and what it actually means. for practical quantum computers. Verification of results by classical computer would also take. See, what is done is, you run a process through a random circuit, a quantum circuit, and then you do a measurement, you get an output. Then you repeat the same process ad nauseum through the same random circuit, and then you will get the probabilities of various outcomes. And then you have to compare this outcome with an ideal quantum computer, under the premise that the quantum computer you have made is not the ideal thing actually. So what do we compare it with? We can take one quantum computer and benchmark it against another. The benchmark that they use for the cross entropy benchmarking is actually suited for that. But what they're not doing that. What they're doing is they're doing a benchmarking of their quantum computer along with what the theory quantum mechanics says that. And who verifies it? A classical computer has to verify that. And a classical computer will take several years, and therefore the verification would take as long as well. And therefore there's no way of directly verifying Google's claim other than some jugaad that they are doing. So this has to be clearly understood. Now, quantum supremacy claim is a bit of a dicey thing. One has to make a distinction between quantum supremacy and quantum advantage. Quantum supremacy says that my algorithm need not do anything useful at all, like the random circuit sampling. It's absolutely useless for any practical use. But in principle, quantum mechanics with resources such as entanglement and superposition is capable of doing what classical resources cannot. We already know that. The world functions by the rules of quantum mechanics. You will not have a semiconductor, a superconductor, a magnet, and I would go through this floor if quantum mechanics were not to work. So, but what is important in this claim is that I make a quantum computer, I engineer one, a circuit-based quantum computer, not a simulator, not an annealer, and then say that it works nearly as good as what the theory does. This is the benchmarking that they do. Now, the validity of this claim needs to be carefully examined. Okay. Then they are using something called a cross entropy benchmarking. I will come to that. So we need to understand these terms if you have to understand what actually Willow does. Error correction is done through something called surface code. Surface code is just the process whereby you are having a logical qubit. Let us say you have a classical computation, then we have a 0 represented by multiple zeros and a 1 represented by multiple ones. And supposing 1 0 is represented by 3 zeros, the logical qubit is 0 and is represented by 0 0 0. And the logical 1 is 1 and is represented by 1 1 1. The physical qubits are the 0 0 0 1 1 1. And a bit flip in one of them can be easily detected. It will correct for one error. Identify, correct for one error and no more than one error. Otherwise you have to then make it larger. Now we have to find its analog as far as you calling sir? Amit is calling me. So that is what we need to understand. The surface code, there is something called a code size, and I will come to defining what a code size is. What they have done is make a distance 3 code, distance 5 code, and a distance 7 code with the Willow. And they say when they go from distance 5 code to distance 7 code, actually the physical qubits have to be increased. Now more qubits you add to define one logical qubit, each of these additional qubits called the ancillary qubits are themselves going to be a source of error. What the Willow has decisively shown that when you go to from 5 to 7, you are not overwhelmed by the errors that are flowing from the physical qubit, but the logical qubit is much more resilient and does better. That is that lambda claim there. When I compare d equal to 5 and d plus 2 is 7, I have something called a p threshold by p. A p threshold is the threshold noise of a single component. If your noise level of your hardware is above this threshold, simply you cannot do any error correction. That is a useless piece of hardware. So now we are faced with how to reduce that threshold. And Google has done a splendid job with their circuit in reducing the physical threshold, but they are way below what we require to do practical problems. So that we will look at. And 2.14 resilience in terms of increment is a very good thing as far as, and it's a good news. In the sense you add more and more physical qubits, you will actually have more and more robust logical qubits. Then we have to look at what is the error rate per cycle. When you do a cycle of these quantum computing, these errors have to be identified. And in quantum mechanics, you cannot look at a qubit and say whether it is 0 split to 1 or 1 to 0. Because an observation will destroy the qubit. You cannot clone the qubit either. So these two things put a restriction on what you can or cannot do with that. So we have to find a way of trying to do this. And identify the errors and correct for those errors. That identification is done through a syndrome. People who are familiar with classical cryptography and other things, you know what a syndrome is. I will shortly explain it. And the error correction syndrome has to be corrected by a classical computation. This is what I was telling Professor Nath, that unless you have ultra fast classical computation that will within one cycle do this identification and correction, feed it back into the quantum computer, this error correction will fail. So quantum computers will work in tandem with classical computers, which you need for error correction. That's the main message here. When decoding latency time, once you pass on and compute the syndrome to a classical computer, and it has to come back to the result to the quantum processor, that latency time they are reduced to 63 microseconds. We have to reduce it further for practical. So then, of course, this is value evidence of multiverse theory and say where the hell is all the computation done. This is utter nonsense. Total blah. They are saying that this is evidence of multiverse. This is a part of the hype. Fortunately, many of them quieted down on this theory. So I don't know. There's the changing thing.
It's changing.
Yeah, but my GIF is not working. It was making nice faces and animating and explaining it. This will work?
Yeah, there on the computer.
Okay. The animation is very unhappy about this particular thing. So the Willow, to summarize, is a 105 qubit superconducting chip, with which it demonstrated an error character surface code qubit, as well as a new, bigger quantum supremacy claim as compared to the earlier one, which fell flat with a 53 qubit thing, and people showed that classical computers are actually having better fidelity, can do better. That also helped for the boson computing thing that the Chinese Jing Zhang Qing or some and so now there's a renewed claim again based on quantum supremacy to say, guys, we are still in the game and don't reduce your stock market prices. Okay. And in terms of real achievement, the coherence time, T1 and T, there's a phenomenal increase from 10 microseconds to 100 microseconds. That shows the quality of the fabrication. This is what I mean that in India you say, if you think one small group anywhere is going to develop a quantum computer, absolutely wrong. We need a fab. We need people working on the fabs. We need to make our chips. And unless we do that, we will go into a regime of technology denial. This is not proper planning at all. So if somebody has good contacts with the National Quantum, please tell them that they are going about the wrong way. So problems and challenges with quantum computers. Sorry for the spello there. So quantum resources are quantum entanglement and coherent superposition of state, and these are inherently fragile and therefore subject to disruption by the environment, and that is a source of noise. And when you make gates, you don't make perfect gates either, and therefore that is also a source of error. And there is also one more thing that is not very widely known, is that there is a long-term drift in these errors that nobody has identified what it is due to. So these are types of sources. And classically, when an error occurs, we have only the bit flip error. But quantum mechanically, we can have something called a phase flip error as well. So this complicates matters. We have to deal with both bit flip and phase flip together. and also address the fact that device imperfections will be there. So imperfect implementation of gates, supposing I want a gate such as this, and actually you don't get the right data, there will always be some plus or minus delta theta. Similarly, in the phase factor, there will be a plus or minus delta phi. And therefore, whenever you are trying to make a gate, this imperfection is inherent, and this depends on the quality of the hardware. Whether you are doing iron traps or you are doing superconducting qubits, we have to live with the fact that we can never make perfect gates, and we have to take that into account. So, a bit flip error is essentially that which will flip the alpha and beta coefficients, and that is done by a Pauli X, and therefore, when a Pauli X operates on the state psi, it will change it to beta 0 plus alpha 1. That's a bit flip, proper bit flip. That needs to be corrected when it occurs. And then we have the phase flip error, a Z operator acting on alpha beta, and it will produce alpha plus minus beta. If you look at the 2 by 2 matrix, it's very obvious why it's doing that. So, and as I mentioned, there are also in addition long-term terms. Then there is this coherence time T1 and T2, where hardware improvements still have to go a long way. But there's a substantial improvement in what the Willow has done. It's a phenomenal job. Increased decoherence time through proper choice of qubits. And for instance, Umakant here will say my latency times are larger, but then these qubits are slower. So there's a trade-off between interrupt and superconducting qubits. These guys will finish in microseconds, but perhaps interrupt will take milliseconds. But they are much more resilient with interrupts. So build-up of errors, and that leads to whether quantum computers are called scalable. And when you try to scale up quantum computers, you have to add more and more additional physical qubits to realize one logical qubit. And therefore, it is a very important claim that Google Willow is making, that as you increase the code size, you are actually not creating more noise. This they have done it from 5 to 7. Whether it will go beyond that, because we need code sizes of 27, 28, much larger for practical use. We need to go to very large codes involving thousands of qubits. So let me just briefly tell you what is quantum connection. This is just a hypothetical circuit where first we have to create multiple qubits from a single qubit. And because you cannot do cloning of qubits, we sort of entail them through C0 operations that we have through these Pauli X operators. And then these three things will generate a 0, 0, 0 or 1, 1, 1. Depending on the first value, if you put a psi, then 0 will create 0, 0, 0, and a 1 value of that psi will create 1, 1, 1. So this is the way of building redundancy into a quantum state without violating the no-cloning theorem. Now, after that, you want to know whether any error has occurred, whether a bit flip or a phase flip error has occurred. For that, you have to generate a syndrome. Now, you cannot directly measure on those three qubits because you will destroy the state. So, we have to choose some additional, those two qubits, we choose some additional qubits. We call the ancillary qubits or measurement qubits. And then, once you put a Z operator on those things, one can generate, if there is an X operator that has acted on it, done a bit flip, or a phase operator has acted on that, this meters will generate classical values based on which you have an error syndrome and identify where exactly the error lies. And this is very important. So errors occur at a variety of places in preparing the Flusian initial states, and then they occur whenever an operator used. You may be wondering why I still have error correction and there's a plain wire going there. That is because a plain wire is an identity operator. Am I running out of time? No. Okay. So all these levels of error correction therefore have to be taken into account before we can make this quantum useful. Now these vertical lines that you see here are what is called the circuit depth. And this is called the circuit width. And therefore we can generate from this, depending on how many cycles we repeat, some benchmarking called the quantum volume. which is widely used one for computing monocomputer people, but unfortunately it is not the benchmark, not the only benchmark, not even an adequate benchmark. This I want you to remember. So that is the circuit depth and width for you. So we have to go a long way in terms of circuit width and depth for practical computation beyond what Google Willow has done. Now we come to the important part of what Google has done, and for that we need some minimal background on how these corrections are done quantum mechanically. So building logical qubits from physical qubits will build in redundancy, and quantum error correction codes generate logical qubits using a large number of error-prone physical qubits. So every individual gate, every individual component is going to have an inherent noise. Now what is the minimum noise that is there per component is called the noise threshold. If the noise threshold exceeds a certain value, then the demands on error correction ancillary qubits goes up exponentially. So we have to bring that threshold noise down, keep it down. Google has successfully done that up to surface code size of 7, less than 7. We do not know what is going to happen beyond that, and this is to construct one logical qubit. And we require thousands of logical qubits which will be interacting, and they are individual component noises, and we do not even know whether the noises will become correlated. If they do, then error correction will fail. There are no quantum computers thereafter. So noise per component is very important. Noise threshold is important. More importantly, connectivity of the gates is important. And what is the fidelity of measurements, and what is the quantum error correction algorithm that is being employed. Now let me briefly explain to you what we do here. This is an encoder. You start with the site, which is qubit of alpha 0 plus beta 1. And then with this you can create logical states such as 0 logical with 3 physical qubits. So there is one logical qubit, you require 3 physical qubits, and likewise for one you require 3 physical qubits. So we can, this type of circuit is done easily, we can generate these things, and then this goes into this encoder. And then the encoder, thereafter we have to do the what I call the syndrome measurement to identify what type of error is there. For instance, we have this syndrome that only identity operator is acted, which means we reproduce this entire circuit, then we are having a syndrome 0, 0. The 0, 0 are just eigenvalues of some operators or stabilizers, and I will introduce stabilizers shortly. And if there is one bit flip operator in one of the qubits, say first qubit is flipped to 1, then what remarkably happens is the Hilbert space gets split into 2 parts. One, the code space, and the other is the orthogonal error space. Now, when something is in the code space, you would get it stabilizers a +1 value. You would in the orthogonal space, you would get a -1 eigenvalue. So the stabilizers are special operators that do not change the state, logical state, but extract an eigenvalue which will tell you something about the nature of error that has occurred. So we have a variety of these things for bit flip alone. We can introduce such syndromes for phase flip as well. Much more complicated. So the Hilbert space basically is split into the code subspace and the error subspace, and stabilizers, which I shortly described, do not change the state but produce eigenvalues of +1 and -1 based on which you do an error identification. This syndrome becomes a massive overhead that has been computed classically and fed back into the quantum computer, which means that unless you have a very, very fast classical computer and with a very short latency time, including the connections, etc., you will not be able to do error correction. This is a major thing, and as the number of physical qubits increases, you are going to have to go to nanosecond level of classical computation to be able to fulfill this requirement. So most of this material I have taken from this particular paper. I am not acknowledging it throughout, but you can read it. It's a very nice paper. So now I will shortly describe stabilizers, and supposing we have made a logical qubit which is a superposition of 0, 0 plus 1, 1. now I have these Z1, Z2 operators. We should understand this Z1 operator acting on the first qubit, Z2 operator acting on the second qubit. So these are basically tensor products of Z1 times identity plus identity times Z2. So therefore, we will be able to generate a plus one, like I said, if there are no flips, plus one, and it reproduce the same logical state, which is an eigenvalue operation. And supposing an X operator had acted on the logical qubit unintentionally, then you will get a minus one eigenvalue based on which you will do the syndrome identity. That's the very simple idea. So stabilizers are essentially the family of Paulis and their tensor products, and they belong to the Pauli group. And all stabilizers of a particular code must commute with each other. These are two essential conditions for a stabilizer. So these are other examples of stabilizers that we skip this. For instance, the bigger code, which is where you require 4 physical qubits for 2 logical qubits, the distance 2, then we can build more complex, more number of operators. For instance, if I have a state such as this, and we have an error generated by x1, x2, x3, x4, this will anti-commute with the stabilizer Z1, Z2, Z3, Z4. When they anti-commute, they will produce an eigenvalue -1. Similarly, if the errors were here, it will produce a negative eigenvalue with that type of stability. So this is a general technique that is used. I'm sorry if it is very short, but then we will have to do for now. So keep it as a placeholder, those people who don't follow it, and read about it. So now we need to correct not only for, thus far I have shown you only bit flip error, but I also want to correct for phase flip. That's where the topological codes are the so-called surface codes come into picture. Now, in surface codes, you essentially make lattice with units such as this. And with units, there is a control Z operation here indicated by these 2 blue lines. And these are the data qubits, and these are the ancillary qubits that we use. And then we make a measurement of with the Z operator here and with the X operator for this qubit. So therefore, we can now make a mat out of these type of tiling, and then for larger codes build on this. And that's what the Google guys have done. So when you do this, if you have a distance 3 code, there will be data qubits of 9, which is 3 squared, and 3 squared minus 1 measurement qubits will be there. These are the data qubits, these will be the measurement qubits. So that many qubits, extra qubits you will require for doing this error correction, and for data qubits of 9, you will require 8 measurement qubits, and therefore that makes it 17 qubits per logical qubit. So this will keep going up. So the surface code is essentially, again, these open circles denote the data qubits, and these are the measurement qubits, and this is how the X and Z operator act on each other. Fortunately, they commute for us, and therefore they have made these large error correction codes with Z with their 107 qubits system for the random circuit sampling. So that will give you some more details about how this is done. It's a bit technical, so we'll skip that. So first we have to understand what exactly are these random circuit samples. Is it a problem of practical use? I already said it's totally useless. And but other than showing the so-called much acclaimed quantum supremacy, that look here guys, quantum mechanics can do what classical mechanics can do. It's like saying a dog walking on 2 legs can do much better than a dog walking on 4 legs. Things like that. That's a type of claim that is being made here. So random circuit sampling and benchmark and metrics, we need to understand this. So we have quantum circuits such as this with predicate gates. Then you randomly choose to make measurements in this and choose one subset of gates. And then you repeatedly sample this. When you make a measurement, despite all the superposition, entanglement, all that notwithstanding, finally you are going to get only 1 qubit as an output. multipartite qubit. And that would occur with a certain probability. Then you keep on, as long as your patient lasts, keep measuring. And then how many times I got 0, 0, 0, 0, 1, 0, 0, 0, 1, whatever it is, and assign probabilities. And therefore you generate a probability distribution. And now we have to compare that probability distribution with what is the ideal theoretical quantum computer will do. And who will tell me what the ideal quantum computer will do? Classical computer has to compute that in 15 years. Okay. So this is basically it. They use a very, very strange quantity called cross entropy benchmark. And this is a very interesting affair. Like I was saying that I want to compare two quantum computers, 250 qubit quantum computers, maybe made by different manufacturer, or two processors made from a different batch or whatever. And I want to say about the performance vis-a-vis theoretical expectation. But this is not what this case do. What they do is that quantum chip that they made, they generated this empirical probability distribution. Once I have an empirical probability distribution, I have to now generate the theoretical probability distribution. Let me call this as my empirical probability distribution. And then I have to compare it with the theoretical probability distribution. I will compute from the theory, which will take 17 years. Now, so therefore I have to do a DIAT. And I have to compare, and that's a slippery business, compare the distance between this distribution and that distribution. You need a distance measure between two probability distribution, not due to some simpler metric you can generate. So that fortunately entropy does it, we know that, relative entropy will do that. So instead of defining Shannon entropy as Px log of P of x summed over x, we say P of x is the one what we get, and I believe it would be Q of x, which is another distribution, and then find what is the relative distance between this. It's got a relative entropy, and so that relative entropy is used, and this is your Shannon entropy, proper Shannon entropy, Pi log Pi, and then find out the difference. That is called the cross entropy benchmark. And what Google claims is through the cross entropy benchmarking that lambda that they calculate has done phenomenally well in terms of the fidelity, and there is no loss of fidelity, and in fact it will do much more robustly when you increase the code distance. In other words, more and more physical qubits you put in, despite their noise, so long as their noise is below the threshold, your logical qubit will become more and more robust and resilient. This is a significant result from Google. So this is their actual theory. They first did the 3x3 grid, which is a distance code of 3. Then they went to a code of 5x5 grid. This of course has 9 plus 8 number of qubits, and then this has 5x5, 25 plus 24, 49 qubits, and data qubits and measurement qubits. And this is the significant graph that they produce. Error rate actually falls with the code distance. Code distance is defined as twice the number of errors you can correct plus 1. If I correct only one error, for instance in my redundancy code of 000, classically, I can correct only one bit clip error. So if I correct one error, the code distance will be twice into 1, 2 plus 1, which means the distance code is 3, where I will use one logical qubit, 3 physical qubits. So it's called a 3, 1, 3 type of code. So this is a 3x3 code, 5x5 code. And this is a type of scaling from 17 qubits to 49 qubits to 97 qubits, and scaling of the physical qubits happens with grid size based on that formula. The number of physical qubits goes as if the number of data qubits is lambda, and we have lambda squared qubits as data qubits, lambda minus 1 squared as the number of answers qubits, and that will stand for k logical qubits and distance code. All that is fine. So you are able to show this correction. But what does it really you need to make this quantum computer useful? How do we counter critics such as Munni who keep taunting us, your quantum computer cannot factorize more than 3 to 5. So this is, yes, it is, the community has no answer to this question as of now. Why? The answer will be very clear from what I tell you. You look at the actual demand. Okay, the polling gates are reversible case, every quantum gates are reversible, but forget for that. So if I have n such logical qubits, I have the order of n cube totally topological gates, which are having much larger requirement in terms of the physical qubits to realize those gates. And for a problem of shore code to be relevant for cryptography, where I can not break it with classical thing, let us say elliptic curve, somebody mentioned Diffie-Hellman and RSA. For it to be relevant, I need to go to n equal to 2000 bits for me to have to run a short code, and that requires a port distance of 29. Where are we now? 7, and we are assuming this trend of going down will continue, even though you have to handle a port distance of 29, and then continuously get a feedback on the error syndrome or a decoding from a classical computer already is taking 63 microseconds. The order nanosecond by which time the superconducting qubit processes it, before the cycle is over, it has to feedback this data. Else the whole thing crashes. So, which classical computer are we going to use it? Now, Jensen brought a 3-meter wafer also and showed, okay, this is going to be it, guys. All of internet will come under that. So, we are still waiting for this. And this is why Jensen is still interested in quantum computing, notwithstanding his state. He's an interested party, but then he is making a fair assessment. So, you require reasonably 3 to 10 power 11 physical qubits. Okay, that's a huge ask. Conservatively, if I do all the thinking and all that, I still require a few million qubits to realize when all other things are ideal to get n equal to 2000. Now you can do the calculation, what it takes for me to go to a 3-bit or a 4-bit and so on. And unfortunately, it's not very favorable now to talk about these numbers. We are way behind those requirements. So we would require something like 14,500 physical qubits for every logical qubit, and it takes 26.7 hours to complete the exponentiation that is required for the short result. That costs a huge amount of overheads. So we require a few million qubits with ultra-fast latency time for decoding the classical computer. That's the crux of the bad news. Why the claim, despite their technological prowess notwithstanding, is not going to take us anywhere close to the utilizability of quantum. Now, we are not in the process. So I always ask the question, is it a limitation of technology or are there fundamental no-go This I am not able to answer this question yet, but I keep asking this question because there are some critics of quantum computers. They say quantum computers are fake, like Jill Galai, and others, where we are not still talking about the interactions and crosstalk of logical qubits. We are surely a pattern where we have thousands of logical qubits. Next, we assume that the noise that we are getting from a single component will just sum up when I add hundreds of physical qubits. Now we are using entanglement as a resource. These things need to be entangled. Who gives you the guarantee that these noises will not get correlated? If they do become correlated, your entire gamut of error correction codes that we use now will fail completely. That may be the end of quantum computing ambitions unless somebody comes with some really ingenious method of correcting for errors or topological qubits become realized or whatever. So These are the problems. So, finally we come to the practical utility of quantum computers. Goal of using it to efficiently solve problems of practical value which are computationally hard for classical computers. When we say efficiency, whether it scales polynomially with the size in terms of computational resource, maybe time or other resources, or is it super polynomial or even exponential? This is the typical classical computing complexity argument that we are using, polynomial, NP, hard problems. So there isn't anything that says that we'll be able to handle NP hard problems with the problem. So it is certainly not going to do that, but theoretically. So now quantum supremacy as claimed by Google is a demonstration of an efficient solution by a quantum computer for a problem that has may not have and does not have any practical utility, like the random sampling with the HCB label. And this is what Willow was claimed. So quantum utility is quantum speed up for solving practical problems. Whether in cryptography or in aerospace or in pharma, whatever, drug design, whatever. These are the things we are interested in. And okay, this is what the Google Willow is. Is a cool kangaroo wearing shades, jumping up and down. How is it going to help me? A bloody donkey which is slow still carries a load from point A to point B. Classical computers are doing very well. Thank you, but they don't jump high because a donkey is never been intended to jump up and down like that. Now, can quantum computers, therefore the cool kangaroo, solve this quantum mechanical problem? Being a quantum computer, this is the question that we need to ask. That is the question related to utility. Now, the quantum community doesn't want to be asked these embarrassing questions. Otherwise, the stock market will suffer, and we will not get funded by NPU. Even otherwise, I'm not getting any funding from NPU. So, what should we do there? The moment the kangaroo carries a load and outperforms the donkey carrying a load and still able to jump higher and move faster, I say, yes, guys, congrats, we have a quantum computer that takes this. Thank you for your attention. I'm sorry I have to rescue that serious part, but one has to spend maybe 10 hours of lectures before one can really compare what.
One question.
Yes.
Launched its first computer, basic computer,
Yes.
what we call classical computer, 3-story building. This room was full of valves and diodes. Each one has one Nobel Prize
Yes.
over the 200 years. That's all came up to 1925. Now, my mobile is 100 times powerful.
No, I understand where you are getting at. Yes, time. And it's premature to discard it now. We cannot even anticipate. I'm not a soothsayer here, saying that quantum computers will never come. I'm just making an assessment as of now. So certainly I'm not saying the fact that quantum computers could eventually become useful or some major breakthrough can come. This is why I'm a fence sitter. But what I'm trying to point out is the phenomenal difficulty and the direction in which we need to head. Granted, from tubes to diode with this bigger crystal, germanium crystal that was demonstrated, to now having billions of transistors on a single chip, and we have gone to nanometer line with, yes.
70,000 switches, the processor.
Jensen, he says that 20 years is a reasonable time, guys. You are not going to get, and he should not be castigated for making a mistake. I entirely agree with you. That's why I asked this question: is it a technological issue, or are there fundamental no-go theorems where physics tells you it cannot be done? I am rather interested in the latter question. Because the technology, we cannot predict it. I've been trying to look for
the application, now day to day we are virtually connecting. What Microsoft doing it, it's almost ahead. We need to catch up with those all. So thank you very much for giving me the opportunity.
And I agree with you. I mean, You will be able to go to a vegetable vendor and click and pay my. These are all phenomenal things that have happened during my lifetime. But
Just a little
Yeah.
comment.
yes, yes. Usha, I'm very happy to have you.
About stock being troubling us.
Yes.
There is quantum finance also which is coming up now,
Oh, yes.
where their models, we
Correct.
may have quantum utility
Yes.
in some other section which we may not anticipate.
Correct, but
So-
see, my son brought to my notice that actually chimpanzee throwing darts is actually doing as well in terms of its predictive ability as compared to some of those models. Now, machine learning is not a thing, in my opinion, because it's artificially then trying to put machine learning with quantum and they don't gel well in terms of our modeling. So this is what I've seen. That's the one reason why we didn't invest any time into machine learning. Algorithm development, yes. But this seems to me to be a very artificial problem for me as such. If you want to bet on finance, I mean, a lot of moolah is there. Obviously, one would like to develop those things. But I don't know. As far as machine learning with quantum, the only place where I see that happening is in quantum chemistry. Quantum chemistry.
Oh,
Because we have been doing quantum chemistry without calling it that, because we have been doing DFT calculations for eons. Now the question is explicitly whether you are going to use quantum resources such as superposition and entanglement other than the actual quantum mechanical calculation to enhance it. And we are going to use, see, machine learning techniques can be separately used. They are very, very useful. And then from a set of candidates, potential molecular candidates, whether it will help us identify possible candidates faster. There is a promise. But I don't believe.
yeah, I agree with you. It's like, what are we going to do with the focus?
Correct.
And how we show quantum.
Correct. But this hybrid donkey kangaroo animal, I am not a voter for that. I'm sorry. Yeah, I'm happy. Finally, we have you at the end. Yeah. Any questions? Yeah, feel free. I mean, students, any question is okay. Yeah.
Sir, this random sampling is in computational complexity is anti-complete, and there is a class. So if we map something, won't we? We can find some use.
See, the question is, yeah, if you establish some problem, to be in NP, then you are right. If you have one NP complete
They are
problem,
polynomially
then
connected.
yeah, polynomially they are connected. That's all the overhead you require. Now, whether this random sampling is, it is an NP hard problem, seems to be, appears to be. But the physical resource requirement is what is overwhelming here. And random sampling seems to be a success as far as this particular claim is concerned. With the proviso that we have to take the other source of noise, correlation of noise into account. That's why I see this as an advance. But yeah, good question. Anything else? Yeah, well, thank you very much for being patient. Yes, ma'am.
Quantum supremacy or quantum utility are not the right things.
No, quantum
Quantum
supremacy is not.
supremacy is
Quantum
not the
utility
right
is what you
thing to
should look
measure.
at. You should look at quantum utility.
Okay.
And I am only talking about the distance, very long distance. We are in for a big marathon before we get into it.
But for the short term, what kind of parameters or measures or metrics will you suggest then? If this
No,
is
see,
not the right one?
No. See, in terms of measures, metrics, benchmarks, there are many benchmarks, starting at a qubit level to a more holistic level. No, I am not talking about the merit or demerit of this type of benchmark. But if I understand your question correctly, instead of going to doing the shore problem, which we know is very, very hard, are there other problems where reasonably smaller? Say if I go to not core distance of 27, maybe 13. There are some useful problems I can still do. The problem there is we don't have algorithms. There are maybe 100 odd algorithms, but most of them are based on the fundamental ideas of Shor and Grover. If you ask, are they fundamentally very different? No. They are based on discrete Fourier transform and things like that. So we still need to work on algorithms. This is one reason why we want to invest more effort into developing new algorithms. Algorithms that can make do with error-corrected quantum computer that are smaller. Maybe that's where we should be looking for in the near future.
That will be for the medium term.
Medium term, that's what we should look at. I mean, it's a personal opinion, I'm not an authority in that, but it's my view. Yeah, if there are no further questions, I thank you all.
Lightning presentation. We appreciate the forward-thinking vision you've shared with us today.